Hello, and welcome back to EEforEveryone. Today we're going to talk about capacitors. Capacitors store energy. You apply voltage to them, sometime later they're fully charged. This energy can be later pulled out as current. As you pull current out of a capacitor, the voltage drops and vice versa. An ideal capacitor doesn't ever consume any power, it simply stores it and then releases energy. You can picture this action kind of like a water bottle or a coffee cup being filled and emptied. The bottle or cup doesn't produce or consume any water, it simply contains it for later use. A capacitor can be really simple. In fact, I've made one at home before. The basic concept behind a capacitor is that if you have two metal plates and you bring them close together without allowing them to touch, a charge can accumulate on the metal plates. This charge induces electric fields that store energy within a capacitor. Now this is dead simple, in theory. You can construct one of these using a sheet of glass and a couple sheets of aluminum foil glued to either side. The equation for a parallel plate capacitor is shown on screen. This equation is generally used for general conceptual conversations about how capacitors work. Capacitance is equal to the dielectric constant times the permittivity of free space times the plate area divided by the distance separating the plates. The permittivity of free space is 8.854 times 10 to the negative 12 farads per meter. So let's think about this for a moment. We can buy surface mount 0805 resistors with a value of 100 microfarads. Micro is an SI prefix that means times 10 to the negative 6. In other words, the capacitance value can be read as a decimal place, 3 zeros, and then a 1. The constant in our numerator, the permittivity of free space, is 8.85 picofarads per meter. This is approximately 9 times 10 to the negative 12th, or a decimal point, 11 zeros, and a 9. The difference between these two numbers is a factor of 11 million. If we assume this is a parallel plate capacitor built in air, K is approximately 1. That means this factor must be achieved with the ratio between the plate area and the distance between the plates. Or in other words, the plates need to be really close together, really big, or both. Okay. With the ceramic capacitor I mentioned before, an 0805 package measures as 2 millimeters by 1.25 millimeters, and the package is 1.45 millimeters tall. Assuming there's only one plate inside that capacitor, the largest plate dimensions we could have is 2 millimeters by 1.45 millimeters, or 0.0000294 meters squared. Uh-oh, our work just got harder. Since our plate area appears to be less than 1 square meter, that means that our plates will need to be even closer together than we originally thought to achieve the ratio. Assuming that the assumptions we've made so far are valid, the two plates inside this part would need to be no more than 26.1 picometers apart. For reference, a helium atom has an atomic radius of 31 picometers. That's right, our plates would need to be closer together than the smallest atom on the periodic table. So what does this tell us? Well, this tells us that the capacitor I'm looking at the datasheet for is not made of a parallel plate capacitor in free space. Oh, you wanted a useful answer. Give me a moment to collect my thoughts. Before I start drawing conclusions and start trying to explain things, there's something you need to know. These capacitors are MLCC parts. MLCC stands for Multilayer Ceramic Capacitor, and the name isn't an inside joke or a trick or something. An MLCC is constructed of many layers of conductive material separated by many layers of an insulating material. I'll let you guess what type of material is acting as the insulator. A ceramic capacitor like this could typically have a tolerance of around 5%, and a voltage range of 50 volts without getting too fancy. A part like this in an 0805 package could have a value of 0.1 microfarads without getting too expensive. Now let's compare this 0.1 microfarad capacitor to the 100 microfarad capacitor. The 100 microfarad capacitor has a 20% tolerance instead of 5. It has a 4 volt rating instead of a 50 volt rating. And the larger capacitor costs 33 cents per unit at a quantity of 3,000 instead of 3 cents at a quantity of 4,000. Now in order to increase the capacitance from a value of 0.1 microfarads to 100 microfarads, or a factor of 1,000, we need to tolerate 4 times as much variability in the capacitor value, apply less than 25% of the voltage, and pay 10 times as much. What in the world is going on here? Now I admit that I could be misled by marketing tomfoolery, but based on the mathematical relationship we talked about before with regards to a parallel plate capacitor, these numbers are painting a clear picture for me. Let me get out my paintbrush. Every material has its limits. An electrical insulating material, such as ceramic, can withstand a certain voltage before it breaks down. In other words, it can resist current flow as long as the voltage doesn't get too large. As a material gets thinner, the amount of voltage it can withstand gets smaller. The material that is providing this insulation in a capacitor is a dielectric. There are some key differences between a dielectric and an insulator, but that isn't too terribly important for what I'm trying to say right here now. To put this relationship between withstand voltage and dielectric thickness in perspective of our capacitor, if we're using a similar dielectric material and the plates need to get closer together, that dielectric material must be thinner and therefore wouldn't be able to withstand as large of a DC voltage. So that explains why the voltage rating of the larger value capacitor squeezed into the same package size is lower. There must be more plates inside of the larger capacitor to achieve a higher capacitance, which means that these plates must be closer together since the physical capacitor size hasn't increased. Okay, technically the 100 microfarad capacitor that I'm looking at is almost twice as thick as the 0.1 microfarad capacitor I'm looking at. Given the capacitance increase of 1,000 times, there would still need to be enough additional plates closer together inside of the 100 microfarad capacitor such that the total plate area divided by the plate separation distance is 500 times larger than it was for the 0.1 microfarad capacitor. So that explains the voltage rating. What about the tolerance? Don't worry, this answer is easier to grasp. The manufacturer of this capacitor makes many different values of capacitor. These capacitor values don't require plates that are incredibly close together, as opposed to the 100 microfarad capacitor we're talking about. So, as we're trying to make these more dense capacitors, the plate spacing will approach the limits of their manufacturing process used to create them. Generally speaking, as you push a manufacturing process to its limit, it tends to have more variability. Hurting things more, the same absolute change in plate spacing, measured in meters, will change the capacitance value more as the spacing gets smaller. For example, if we have a nominal thickness of 5 meters with a tolerance of plus or minus 0.1 meter, the thickness has a tolerance of 2%. If this were 1 meter with a variation of 0.1 meter plus or minus, the thickness would have a tolerance of 10%. Therefore, it's easy to see a reason why the larger value capacitor with plates closer together might have a larger tolerance if it's near the limit of the manufacturing process. It's also reasonable to conclude that the reason why we can't purchase a 100 microfarad 0805 capacitor with 1% tolerance may simply be because nobody can reliably manufacture them with yields high enough to be profitable. This leads us to the cost. Since this 100 microfarad capacitor may be closer to the limit of the manufacturing process than the 0.1 microfarad capacitor, the yields will likely be lower for the more complicated part. If you put the same amount of work into producing something but have less of them when you're done, you need to charge more for this more complicated item to still make a profit. I don't have experience with capacitor design or manufacture, so I can't talk about the specific issues someone might run into when trying to build a multi-layer ceramic capacitor. I suppose I could say something, it might not be right and I'm guessing, and I don't want to mislead you. If you have experience with designing or manufacturing ceramic capacitors, let us know in the comments and we'll talk about it. We've discussed some basics and background information about capacitors, taking a slightly closer look at multi-layer ceramic capacitors. There's a lot more going on inside of a capacitor and many aspects of capacitors that we haven't talked about. However, as you might have noticed, I've been talking for a while, so we should move on. If you haven't noticed, then I think that something is probably wrong. If you haven't noticed, then I must be doing a good job. Let's round out this discussion by mentioning parasitic capacitors. A parasitic capacitor is not like a regular capacitor, except for you might not have intended to put it there. If you have two metallic objects separated by something non-conductive, like paint or the air, they are coupled by capacitance. The value of this capacitance might be small, but it is there nonetheless. While capacitance can store and release energy when charged and discharged with DC, when AC is applied to a capacitor, it behaves more like a resistor whose value depends on frequency of the signal applied to it. That's a whole can of worms right there. Let's circle back to that after we introduce the frequency domain. I don't want to oversell anything, but the frequency domain will fundamentally modulate the way that we analyze signals. Parasitic capacitors can also be formed on a PCB by placing copper traces above one another on adjacent layers. This is usually a bad thing, unless you intend to create the capacitor. Parasitic capacitors can cause crosstalk and distortion of signals running through a PCB. Sometimes matching transmission lines for high-frequency signals can be achieved with stub transmission lines on a PCB, since parasitic resistance and inductance of a capacitor is working against us at high frequencies. These transmission lines aren't exactly a capacitor, but they behave like an ideal capacitor of a certain value at a specific frequency. Sometimes the parasitic elements of a component can overpower the expected function of the component we intended to solder to the board, depending on what frequency we're operating at. I'm going to be totally honest here. It's going to be a long time before we can break out the Smith chart and really do this topic justice, but it just felt wrong to leave out completely since it's so cool. You should subscribe, and maybe we'll get back to this topic in a few years. I hope that you enjoyed this video about capacitors and better understand what they are. If you would enjoy designing a PCB to highlight how parasitic components can help or hurt us when designing a PCB, let me know in the comments and we can do that. In a future video, we'll talk about the parasitic resistance and inductance found in capacitors, their frequency-dependent impedance, and a few practical uses of capacitors in circuits. If you think this video is great, please let me know by hitting the like button, subscribing to the channel, and leaving me a comment telling me what you enjoyed. Most of all, I hope that you learned something great today, and I hope to see you again soon. Bye!